Now that we have discussed things like domain and intercepts and multiplicity of zeros and how that affects what happens at an x-intercept, and we've discussed vertical asymptotes, holes, and oblique asymptotes and horizontal asymptotes, etc., we can now put these all into practice by looking at the graph of a polynomial function. So whenever you are given a polynomial function and the goal is to graph, one of the first things that you can do is find the end behavior of the graph. And that is, of course, determined by looking at the leading term whenever it's in standard form and looking at the power function that results from that. And then we know that the end behavior of our function will have the same end behavior as the power function. Then we can look at the intercepts of the graph, so the x-intercepts and the y-intercept. And we can look at the multiplicity of the zeros to look at what happens at the x-intercepts. And then we know from the degree that the maximum number of turning points is going to be n minus 1, where n is the degree of your polynomial. And this would also correspond to the relative extrema that you have. And then we can choose x values between and beyond any x-intercepts. So let's take a look at an example. Here we have a function, and notice that it is already factored. So whenever we go to find the end behavior of our function, we have to pretend to multiply it out. So let's do that. So if we are looking at multiplying this out, we would have negative 2x squared times x. Notice that's x to the first, x to the second. So f of x will equal negative 2x squared times x squared plus some additional terms. So this will be negative 2x to the fifth plus something. So the power function is y equals negative 2x to the fifth. And that's an odd degree. So with an odd degree, we know that our function in behavior will look like this or like this. How do we know which one it is? Well, it's a negative leading coefficient. So that narrows it down to this one. So the end behavior is as x approaches negative infinity, f of x approaches positive infinity, and as x approaches positive infinity, that means as we're going to the right, what does y do? F of x, which is y, goes down. So there's our end behavior. Now let's find our intercepts. So if we are going to find our x-intercepts, this is particularly nice because we are already in factored form. And so we can look at the factors. So our x-intercepts are x equals 0, x equals 1, x equals negative 5. Now for our y-intercept, we know that we can just let x equal 0. So f of 0 equals negative 2 times 0 squared, 0 minus 1, 0 plus 5 quantity squared. So we get 0. So our y-intercept is y equals 0. Now the real zeros have multiplicity, and then that corresponds to x-intercepts, which corresponds to behavior at the x-intercept. So our first 0 is 0, so that corresponds to an x-intercept of x equals 0. The multiplicity is 2. Then we have a 0 of 1, which has a multiplicity of 1, and so our x-intercept is 1. And then negative 5 has a multiplicity of 2. X-intercept would be x equals negative 5. Now, to determine behavior at our x-intercept, multiplicity that's even would mean that we touch at the x-intercept. And then a multiplicity that's odd would mean that it crosses at the x-intercept. And so negative 5 has a multiplicity of 2. 2 is even, so it touches. So how many turning points could we have? Well, the degree. Well, we can look back at our power function, and remember the power function was y equals negative 2x to the 5th. So the degree is 5, so that's n. So the maximum number of turning points is always 1 less. So 4. Now we can put it all together. So we remember that our end behavior should look like this. And so whenever we go to graph, that'll help us out. So let's go ahead and put on our graph our key points. So we had 0, 0, we had 1, 0, we had negative 5, and that's our x-intercepts and our y-intercept. And we know from our end behavior that we're going to be coming down to this point, and then at negative 5 we touch, so we're going to come back up, and then at 0 we're going to touch again, we're going to come back up, and then at 1 we're going to finally cross and we're going to go down. So if I did nothing else at this point, we would have something that looks like this. But what we can do is now we can plot some additional points to see how much we go up to the left of this, negative 5, and between negative 5 and 0 we can get another point, and then between 0 and 1 we can get another point, and then to the right of 1 we can get another point. So we're going to get additional points between our x-intercepts and then beyond our x-intercepts. So let's make a table of values. So if we go beyond our negative 5, we could choose negative 6. Between negative 5 and 0, we could choose negative 2. It doesn't matter as long as it's between negative 5 and 0. And then between 0 and 1, we can choose another value, say 1/2. And then to the right of 1, we could choose 2. And then we merely substitute these x values into our original function. So go ahead and determine the y values for each of these. So for negative 6, we obtain 504. For negative 2, we obtain positive 216. And then for 1/2, that's 121 over 16. But we should probably approximate that since we are going to be putting this on the coordinate plane. So this is about 7.6. And then whenever we put 2 in for x, we obtain negative 392. So let's go ahead and put these values on our graph. So negative 6 is at about positive 504. And then whenever we look at negative 2, we got 216. And And then for 1/2, we have about 7.6. So that's really low. And then for 2, we have negative 392. So let's go through the points now. Remember that polynomial functions are continuous and they're smooth, so no sharp turns. This is going to be just barely above our axis. That's probably even exaggerated. And so there we have it. I'll erase the green curve now. It's amazing, though, how much we could see without even plotting any additional points. That green curve matched pretty well. Another thing to notice is that we said that we had a maximum of 4 turning points. So if we look, our turning points always correspond to relative extrema, or simply where we're switching from decreasing to increasing or vice versa. So where are the turning points? Now, I have some points on here. This may or may not be a turning point. It's just a point that we graphed. To find actual turning points, we have to do calculus. So in my sketch, we have a turning point here. We have a turning point somewhere in here, here, and then somewhere in here. So we have 1, 2, 3, 4 turning points. And so that obeys the fact that we're supposed to have 4 or less turning points. Now let's look at another example. So here again, we have a very similar setup. Our polynomial is factored. So let's begin. So if we're looking at our power function, y would equal x times x squared times x squared. X times x squared times x, which is squared. So this is y equals x to the 5th. So the end behavior is based upon this power function. So since it has an odd degree, we know that we are looking at behavior that looks like this or this. Since our leading coefficient is 1, which is positive, that means we're looking at this one. So the end behavior is as x goes to the left, as x approaches negative infinity, what does y do? Y goes down, so negative infinity. As x gets big to the right, what does y do? It goes up. It gets large. Now let's find the x-intercepts. So now for x-intercepts, let's take a look. We are looking at these factors. So if we're looking at the factor of x, then we know that the x-intercept would be x equals 0. What about x squared plus 2? X squared plus 2 equals 0 is not a linear factor. If we tried to solve that, we would have x equals plus or minus the square root of 2i. This is not real. So since it's not a real 0, there is no corresponding x-intercept. So then we have x equals 3. So our x-intercepts are x equals 0 and 3. What about our y-intercept? Let's let x equal 0. So f of 0 equals 0 times 0 squared plus 2 times 0 minus 3 quantity squared, which is 0. So our y-intercept is y equals 0. Now let's list the real zeros, their multiplicity, and then determine the x-intercepts and the behavior. So the real zeros are x equals 0 and x equals 3. The multiplicity at 0 is 1. I'm looking at this x, and notice its exponent is 1. That's how I'm obtaining the multiplicity. And then x equals 3 has a multiplicity of 2. That's obtained from the exponent there. So the x-intercept corresponds to the real zeros, and then the behavior at the x-intercept is based upon the multiplicity. So multiplicity that's odd, like 1, we're going to have a graph that crosses. And if our multiplicity is even, then it touches. So here, we've already seen the power function has a degree that's 5, and so does our function. So that means that the maximum number of turning points is 1 less. So it will be 4. So let's go ahead and graph. So we know our end behavior is going to look something like this. And we know that our x-intercepts are 0 and 3. Now we know that at 0 we are going to cross, and we have to obey this end behavior. So we must be coming from down below, and then we're going to come up, and then we're going to go to our 3, and then at 3 we're going to touch, and we're going to go up. So notice how that obeys the end behavior. This would be really good, but we can get better by plotting a few additional points. So let's plot some. To the left of 0, we can choose -1. Between 0 and 3, we could choose 1. And to the right of 3, we could choose 4. Again, there are other points you could choose, but these are just a selection. So go ahead and pause the video and see what y values you obtain. So if I substitute in -1, I get -48. For 1, I obtain 12. And for 4, I obtain 72. So here we go. Let's plot those points. For -1, we get -48. So that's somewhere down here. For 1, we get 12. And then for 4, we get 72, which is way up here. And so let's go ahead and sketch. Our green curve matched pretty well. Just needed to be steeper on the right. Erase our green curve. Now, we're increasing to decreasing, so we have one turning point, then we have another turning point. So we only have 2 turning points in this graph. We had a degree of 5, so I need 4 or less turning points.